Last time we talked about stochastic processes and how stochastic differential equations describe their local behavior over time. Today we move on to the stochastic calculus, specifically the Ito calculus. For stochastic processes, we need calculus to solve stochastic differential equations, such as the geometric Brownian motion. Now, at first glance, the equations look like the ordinary differential equations, except that we are having the stochastic process as a function over time. If we look at this equation, it looks a lot like ordinary differential equations. So we might expect to solve it with ordinary calculus. But in this case, it does not. There is something strange happening with the stochastic processes. Namely, the second-order terms matters for the stochastic processes. And because of that, if we apply the ordinary calculus, we get the wrong answer. To understand why, let's just solve the geometric Brownian motion with ordinary calculus so we can see exactly where it went wrong. And just for a reminder, the reason we like to use this equation to model stock price is because the fluctuation is with respect to the percentage. So basically for this equation, we have the change of the stock price over the stock price equals to mu times delta t plus sigma times b delta t. So basically delta st over st is the ratio. It's like the percentage change for the stock. And that is provided by a drift term plus a fluctuation term, so that we can just directly link the mu and sigma to percentage. For example, mu equals to 1% and sigma equals to 3%. So we can model the drift and the fluctuation using the percentage for the stock price. So now let's just pretend we can solve this problem with ordinary calculus. And just to simplify this equation a little bit, let's just ignore the drift term. Let's just say that the differential equation is dst equals to sigma times st times dbt, right? We consider the fluctuation only differential equation. So the first step is that we can do separation of variable. We'll have 1 over st times dst equals to sigma times dbt. Basically, for the left-hand side, that equals to d log of st equals to sigma times dbt. Then we can just integrate both sides, right? Let's say that the bound of the integral goes from 0 to t, and maybe I should just replace the t inside as a dummy variable. So let me just replace that. Let me just replace that with tau. And then we'll have the log st minus log s0 equals to sigma times bt. We can merge the log as the ratio between st and s0. That equals to sigma times bt. And then our basically has st equals to s0 times exponential sigma times bt. So that is the solution. So just saying that the stock price at time t equals to the initial stock price times a factor. And in order to get in a little more intuition, let's just look at this factor here to see what it means, right? Okay, so notice that this factor here is a random variable. But in order to get more intuition, we can compute some properties of it. So first, let's compute the expectation of it. Okay, so the expected value for it, we just need the integral e to the sigma bt times the density function. Then we'll have the Gaussian density So I'm not going to compute this integral, but the solution for that equals to e to the half sigma squared t. So one thing to notice is that the expectation is greater than 1. Or I should say greater or equal to 1. So it just means that when sigma equals to 0, when there's no fluctuation, the factor, right, the stock price equals to the initial price. That makes sense. And if sigma is greater than 0, we have some fluctuation, then the expected value of stock price at time t equals to S0. So it just means that on average, the stock price is trending up. And next, let's also compute the median for this factor. This is the mean. So we're going to look at the median as well. So let's say that the median equals to k, right? It just means that the probability of this random variable greater or equals to k, the probability of that equals to 0.5. So you can just take the log inside the probability as sigma times bt greater or equals to log of k equals to 0.5. And this just becomes a median for the Gaussian distribution. And we know that the median of the Gaussian equals to 0. So it just implies that log k equals to 0 and k equals to 1. So this just means that there will be probability 1/2 the stock price at time t is greater than S0, meaning that we are making money from this stock, and then the probability 1/2 of the stock price being lower than the initial stock price. Okay, so I actually run a simulation for this example. Let's take a look at it. So this is the simulation I did for the geometric Brownian motion that's given by this differential equation. So for this simulation, I set the initial stock price to be $100. And each of the gray line here is a random stochastic process. Then I basically simulated 1,000 times. And then I computed the empirical mean and empirical median using the data. So see here, it does not really match with what we predicted. We notice that the mean actually stays as the initial value, and then the median is drifting downward. So this means that the stock price higher than our initial price with probability smaller than a half. And the probability of losing money is higher than a half. But you see the interesting behavior here is that the winning and losing are not symmetric because there are some cases due to the randomness, the stock price can pump up really high, right? The highest price reaches more than $500 just due to the random chance. So in those paths, we can make $400, but the maximum amount we can lose is just $100 with the money that we put in at the beginning. And because the winning and losing are not symmetric, on average, it cancels out. Okay, so all of that is saying this equation is not correct. But actually, we are not far off. All we need is a correction for it. So the correct formula is ST equals to S0 times exponential sigma times BT. So far it's the same. The minus a half times sigma squared T. So you have one extra factor in here. That's a correction term. So I'm not going to compute the mean and the median for it, but if you do, you'll see that the behavior matches the simulation. So this correction term is the essence of Ito calculus, and we'll look at how exactly it shows up in the rest of this video and perhaps in the next video. Motivated by the strange behavior of the geometric Brownian motion, let's first take a look at the difference between ordinary calculus and stochastic calculus. The main issue is that when we have Brownian motion as the function input, the second-order Taylor expansion can no longer be ignored. Let's take a closer look. For the ordinary calculus, we can also expand the differential into the second order with Taylor expansion. But the thing is that the second order term, the dx square, is much smaller than dx. So that is why we can just ignore the second order term in the ordinary calculus. But for stochastic calculus, for the Brownian motion, we cannot make that assumption. In fact, the square of the Brownian motion over a small period of time equals to dt. So that is why for Brownian motion, the Ito calculus is different from the ordinary calculus. In order to prove this result, let's consider the integral formula for the same equation. So the equation that we just looked at is the differential version. And for the integral formula, we just simply integrate over both sides. Let's say that the range of this integral goes from 0 to t. So this is just going to give us a fundamental theorem of calculus. You have ft minus f0 equals to the integral of the first derivative. Of course, we can also expand this integral into the second order, but the thing is that the second order won't accumulate. So you can write that as half times the second derivative of x, the second derivative of f times dx. But that's equals to 0. So that is the reason we get the fundamental theorem of calculus. Is because only the first order term survives in this integral version. We will show this result later. Then with Brownian motion, if we look at the integral version of the Ito calculus, we'll have we just integrate both sides from 0 to t. Let me just use capital T to distinguish that. Have df of bt that equals to So the main difference here is that the second order term will accumulate, and this is known as the quadratic variation. And then we can swap off this square term with dt. This is a special property for the Brownian motion. In the case of ordinary calculus, the quadratic variation simply equals to 0. So equivalently, this is because dx squared equals to 0, so the quadratic variation equals to 0. In the case of Brownian motion, the square of the Brownian motion equals to dt. So with the integral, we have the quadratic variation not equals to 0. That is something we're going to prove in this video. So for the finite version, right, let's just consider that we have a process from 0 to t. Suppose that our process looks like something like this, and then we're just going to divide this time interval from 0 to t into n different parts, right? So we just divide it with n different parts, where we set the delta t equals to the total time period, capital T, over the number of period n. And for the simplicity, let's just first ignore the integrand. So we're just going to approximate the square of the Brownian motion. So that just equals to the sum of n period times the change of Brownian motion, delta b squared. As for delta b, we use the property of the Brownian motion to know that it is normally distributed with mean 0 and variance delta t. In order to compute this, we can just apply the law of large number here. So the trick is that we can just get the average of it and multiply it by n. So we have n times 1 over n times the sum. And we can just apply the strong law of large number. So it means that this has an almost sure convergence. So that will be n times the expectation of the delta b squared. So the expectation of the delta b squared is simply the variance. So that's just going to be n times the variance of delta b, which equals to n times delta t. That equals to capital T. And that completes the proof. We now see that the quadratic variation is not 0. And using this equation here, we can just write down the equivalent form for the differentials. This quadratic variation equals to capital T, and for the capital T, we can write that as an integral from 0 to capital T of dt. And this just implies that the square of the Brownian motion equals to dt. So this is the intuition behind quadratic variation, and a full rigorous proof requires the machinery of Ito integrals and the stochastic convergence. But this proof right here is the reason why the second order term is not negligible in Brownian motion. So using the formula for the quadratic variation, we can derive Ito's formula. So Ito's formula is saying that when we have a function that takes a Brownian motion as input, so the difference between the function at time t versus time 0, so that equals to the integral of the first derivative plus a half times second derivative we need to include the second order term here because dbt squared is not negligible. The idea of the proof is that we can discretize the integral by breaking it down into n intervals. So this is from 0 to t. You can just break it down into n pieces. So we can just say this is equal to the sum of I goes from 1 to n, and then we'll have the integral from ti to ti plus 1. So these intervals are t1, t2, t0, t1, t2, all the way to tn. Okay, so we just break it down and then we write that, then we copy I prime bt times dbt plus a half times the second derivative times dbt squared. So the problem actually is not caused by the first integral. So actually I'm just going to rewrite this a little bit. I'm just going to combine the sum with the second integral. So we can just copy the first order integral, in fact, from 0 to t f prime of bt dbt. Then we'll put the sum in here. That goes from ti to ti plus 1. Now we can do approximation because if the time interval is small, this second derivative, this function is approximately a constant. So that is so this is approximately just equals to the second derivative of bti, right? So basically it's no longer changing. We can just move it outside of the integral. So that equals to integral from 0 to t f prime bt times dt plus a half sum second derivative bti times the integral of ti to ti plus 1, and then we'll have the dbt squared. Okay, so now we can just apply the quadratic variation, right? So this integral is basically just ti plus 1 minus ti that equals to delta t, right? And then this entire thing here, right, that just become another integral. So we'll have the integral from 0 to t f prime of bt dbt. I think this is bt and plus a half times the integral Now we derive the Ito's formula. For the left-hand side of the equation, we can write that as the integral from 0 to t df of bt. And alternatively, you can just remove the integral sign. We'll have df equals to f prime bt dbt. This is a ordinary calculus plus a correction term of a half times the second derivative times dt. Now we have the Ito's formula. The second derivative shows up exactly because of quadratic variation, which making the dbt squared term equals to dt. And in order to make a comparison, let's just look at the behavior of ordinary functions to highlight the difference. So again, we can just divide the x. This is from x0 to x capital T. You can just divide that into equal intervals. Right, so we can say that delta x equals to x capital T minus x0 over n. And then we can just approximate this integral with a sum. Of the second derivative evaluated as xi. And then we'll multiply that by the delta x squared. Then we can just factor out one delta x outside. Limit delta x goes to 0 times delta x times. We can also factor out the half. And then we can have the second derivative times delta x. And if you look at this equation here, right, that is simply the Riemann integral. So it's just gonna converge to the integral of the second derivative. Right, so it's just gonna equal to the difference between the first derivative. So we will have and that's just gonna converge to 0 because the difference of the first derivative is just gonna be a finite number, right? So that will just converge to 0 as delta x goes to 0. So from here we see that for ordinary calculus, right, the quadratic variation, the second order term doesn't really accumulate. Basically, in ordinary calculus, the second order goes to 0 as well as the higher order terms. So all we left is the first order. Okay, then next, let's look at a little bit more general case where there are two variables involved. This is more relevant to our purpose. In the case of stochastic process, it's common to deal with functions that has two arguments with both time and the stochastic process, xt. So a common setup for this is it's called the Ito process. It's basically that the differential of this process is given by a drift plus a diffusion. For example, the geometric Brownian motion can be written in this way. So for the GBM, so the dxt is simply equals to mu times xt times dt plus sigma times xt times dbt. Actually, the GBM is a special case of Ito process because the drift and the fluctuation only depends on the process xt. It does not depend on time. For the more general Ito process, it can depend both on time and the process. But anyway, let's keep going. So this is a general way we set up stochastic processes. It's with the Ito process. It basically tells us the local evolution of the stochastic process with this equation. Now the question is that how do we find this differential? Notice that this differential here has two arguments as well, one with respect to time and the other with respect to the Ito process xt. So the solution to this is that we can just expand this into the second order using the second order Taylor expansion. So that will be the key thing here is that even though we have three quadratic terms, the only term gonna survive is related to dbt squared, right? Only the square of the Brownian motion is gonna survive. And the dt square is equals to 0, and then dt times dbt also equals to 0. The first term is gonna go away, and the second term is also gonna go away, right? If we just multiply, if we just swap out the dxt with Ito process, we don't see the dbt square in here, right? But for the third one, right, we'll see the dbt square. Okay, so let's just expand it out, right? So let's see that the dxt square that will equals to mu square dt square plus 2 times mu sigma dt dxt plus sigma square dbt square, right? And the first two terms is not going to survive, so all we have is just going to be sigma square times dt. Therefore, we can just write this out as the partial f with partial t dt plus partial f with respect to partial x times mu times dt plus sigma times dbt plus a half the second partial derivative times sigma square dbt square. And the dbt square is we can replace that with dt. Then we can also merge the dt terms and dbt terms. So it's just going to give us partial f partial t plus partial f partial x times mu plus a half partial, the second partial times sigma square dt plus partial f partial x times sigma times dbt. And that equals to df, right? So this is the key equation for the Ito calculus. So as you can see that the Ito process is actually governed by a stochastic differential equation, right? If you look at this equation here, right, the Ito process. So if you look at this equation here, the Ito process, right? So because both sides involve the process xt, right? So that is a stochastic differential equation. So the SDE tells us the local evolution of one particle or one stock, right? This is a macroscopic level that we talked about. Now we can think if we can solve the stochastic differential equations directly. So the solution of this can tell us the evolution of one particle or one stock along a single random path. This is something we're going to look at in the next video. We'll solve the geometric Brownian motion as a SDE with Ito calculus, from which we'll get the correction term for the downward drift that we see in the beginning example of this video. This is still unfinished, so I'll see you next time.